Okay, hi everyone, welcome to this evening's video. Today we'll be continuing our discussion about firewalls, the TCP IP suite of protocols. TCP IP is a suite of protocols, which means that it is a bunch of protocols that work together. Protocol suite sounds much more sophisticated than protocol bunch, doesn't it? A protocol is a collection of rules that computers use to communicate with each other. Sometimes multiple protocols are needed to communicate, which is not much different from the real world. Suppose that the President of France wants to talk to the President of the United States. Before the discussion takes place, both presidents must agree on a number of issues. For example, they have to decide on whether to use a telephone or meet in person. If they use a telephone, they have to decide which particular aide of the French president will initiate the call to which particular aide of the American president. After that issue is settled, they need to agree on which language to use. They also must agree on the tone of the conversation. Will it be a formal talk or an informal exchange of ideas? And finally, they have to decide on the meaning of what they say. If the US president says that he doesn't like snails, will the French president understand this is a subtle hint about the menu for the next state dinner, or as an attack on the French way of life? As you can see, protocols have several layers too. For example, the lower layers in this example, in the question about whether to use a telephone, only when that has been sufficiently resolved can the presidents get to the higher layer. Like the presence of two countries, computers need to agree on some standards, and it is the protocols that define these networking standards. Furthermore, just as in diplomacy, protocols exist at each level. Starting at the hardware level, an agreement must be made about what voltage to use signal data on a network wire. If no standard is determined, some computers may use 10,000 volts, whereas others expect a signal that uses 1 volt. The result may be entertaining from an observer, but destructive for the computer. Sizing up the competition, TCP IP is not the only game in town. Other network protocols are example, such as IPX, SPX, Inter-Network Packet Exchange, sequenced packet exchange used primarily by Novell, and Apple Talk used primarily by Apple for Macintosh computers. However, these protocols and others are being used less and less as TCP IP is replacing them. Why? Because all major networking vendors support TCP IP, and it's the protocol used by the internet to connect millions of computers around the world with each other. The key word is interoperability, which means that TCP IP lets your computer talk to almost all other computers. TCP IP doesn't really concern itself with the physical signaling characteristics of the transmission media, the cable type, the electrical voltages stuff. Indeed, it works over a number of transmission media, such as cabling, telephone lines, and satellite links. Instead, TCP IP deals with how data is put into packets, where are chunks of data with additional information that is needed to be delivered the data correctly. Think of a data packet as a letter that you drop in the mailbox. You write information about the sender and recipient on the outside, add information about special delivery options, and put whatever you want to send into the envelope. In the same manner, a network packet contains information about the recipient and the sender, special options, and the data that needs to be delivered. And just as the postal service doesn't care about the contents on the envelope, TCP doesn't care about the contents of the packet. For example, if you send an email, TCP IP is concerned only with delivering the packets that make up the mail message. It doesn't care about the mail message itself. History of TCP/IP. Sorry, that should be T there. TCP/IP was originally developed in 1969 by a US government agency known as DARPA, Defense Advanced Research Projects Agency. The goal was to develop network protocols that would allow communications between military computers over an unreliable infrastructure. The idea was that if part of the communications capabilities of the United States were destroyed in a war, the rest of the network would not be affected. For example, if a direct link between two computers became unavailable, and there was still an indirect link via a third computer, TCP/IP should be flexible enough to allow automatic rerouting of network traffic via this alternate connection. Because of the links between DARPA, later renamed ARPA, and leading universities, TCP/IP became the network protocol of choice for many university networks, and eventually it became the protocol suite used for the internet. Most of us are not too concerned about how the US military infrastructure will survive a large-scale nuclear war. However, because of the roots of TCP/IP, the internet today uses a set of protocols that can function well in an environment in which there is no centralized control, there is no constant risk of partial network outages. For example, suppose that construction workers dig a trench and accidentally destroy a buried network cable that connects two parts of the country. As a result, some computers may not be able to communicate with each other. However, most of the internet will continue to function, and most network traffic will get rerouted automatically. TCP/IP also allows the internet to grow at a rapid rate. The internet started out with only 5 computers. Today it encompasses millions of computers and other devices. During the 1990s, the military pulled out of the business of managing the internet. For a while, the National Science Foundation ran it, but the government quickly turned over most management and infrastructure tasks to private companies. At the same time, people outside the military and academic institutions became aware of the internet and realized that it could be used for a whole range of things, from sending email to shopping, from listening to radio stations on the other side of the world. Although the TCP/IP protocol is showing signs of strain in dealing with this growth, overall, it has held up very well to the tremendous growth of the internet. In technical terms, it has scaled rather well. So protocol layers. When we looked at protocols earlier in this chapter, we used the analogy of a conversation between the presidents of two nations. We saw that multiple layers of communications are involved and that protocols exist for each other. TCP/IP also involves several layers of protocols. Different parts of the networking software or applications on your computer are responsible for processing the information inside of the layers. As far as TCP/IP protocols are concerned, there are 4 layers. Network layer interface. This layer, which is sometimes also called the network access layer, deals with all the protocols that determine how a network packet is sent across a given physical network infrastructure. The TCP/IP protocol specifications cover only portions of this layer. Basically, you can use any network structure that you want, such as Ethernet or a satellite connection. If TCP/IP were the postal service, the network interface layer protocols would define how the letter carriers load their vehicles and what kind of trucks they transport the letters. Internet layer. This layer is concerned with giving each computer in a large network a unique address and being able to route all packets to a computer based on this address. If TCP/IP were the Postal Service, the Internet Layer protocols would define the format for envelopes and how postal codes and street addresses are used to deliver a packet. Transport Layer. Protocols at this layer are responsible for data integrity. One of the functions of such a protocol is to ensure that all packets for a given transmission are received. If not, the protocol may request that the originating computer send them again. If TCP/IP were the Postal Service, the Transport Layer protocols would be responsible for keeping track of registered mail, ensuring that letters are received intact and notifying the sender if a letter did not arrive. Application Layer. Protocols at this layer are responsible for implementing specific applications or programs. For example, email protocols define what command a mail program sends to a mail server to retrieve email messages. If TCP/IP were the Postal Service, application layer protocols would define what you are allowed to place inside an envelope and perhaps even the language in which a postcard must be written. Address basics. Just as you need telephone numbers and addresses to send messages to your friends, computers need addresses to reliably communicate with each other. Take a look at some of the addressing schemes and how they're used. Hardware addresses. Each network adapter that is used on an Ethernet network is identified by a unique hardware address that is contained in the electronics of the network adapter. The adapter's manufacturer ensures that the hardware address is unique and not a duplicate of the hardware address of any other computer in the world. The uniqueness of the hardware address is designed so that network traffic for a computer is always received by that particular computer. This addressing scheme works well on a small network, but it has severe problems in a larger environment. Without a worldwide directory of all network cards that have ever been produced and the location where they are operating, there is no way to route information to the correct card. After all, even though hardware addresses of two New York cards may be very similar, two network cards could be very similar. One could be in the Arctic and the other one in New York City. IP addresses. With TCP/IP, each address is assigned at least one IP address. Unlike hardware addresses, IP addresses are not guaranteed to be unique, but a good network administrator will make sure that they are. After all, just as having several houses with the same address makes mail delivery impossible, using the same IP address for multiple computers causes problems in delivering network packets. An IP address is comprised of two parts, the network address and the host address. This IP address is just like a postal address that contains a street and a house number. All computers on the same network segment share the network address. The host portion is unique to a computer on that segment. Routers, which are devices that move network packets between different network segments, have enough knowledge about internet addressing to move a packet to the correct network segment based on the network portion of the IP address. After the packet arrives on the correct network segment, it can be easily sent to the recipient. IP addresses are normally written in dotted decimal format, which means that they are comprised of four numbers with dots in between. For example, 192.168.1.200. Each of these numbers can be between 0 and 255, which are all the decimal numbers that you can create with 8 bits. DNS names. Computers like addresses that are comprised of numbers, especially because an IP address can be expressed in binary numbers, which is the numbering system that computers are built upon. However, binary numbers are not so easy for people to remember. For example, if we told you to connect to a website at the address 208.215.179.139, you would likely immediately forget this address. However, there's a better way to help people like us, the DNS domain name system was developed. DNS is a large directory of names such as www.dummies.com. DNS names are much easier to remember than IP addresses. However, when you connect to a website, your computer looks up the DNS name and finds a corresponding IP address. It works like the telephone directory assistance in looking up a name. Keep in mind that even when you type a DNS name, your computer will eventually connect to the remote computer using an IP address. IP addresses. When you administer a firewall, you have to define rules about what network traffic is allowed to pass through the firewall. Often these rules are based on IP addresses. For example, if your web server's IP address is 23.10.10.7, you may want to create a rule that allows network traffic to that web server. In order to use IP addresses, you should understand at least the basics of how they work. Understanding how they work is much easier when you understand a little about binary math, because that's what computers use when analyzing IP addresses. Don't be scared though. We won't take you back to algebra class. If you made it through second grade, you'll be able to understand how binary math works. What IP addresses mean. An IP address has several characteristics. First, it is unique on the internet, at least if it's correctly configured. That means no two computers share the same IP address. Second, each IP address is comprised of two components, the network address and the host address. This is like a mailing address, which has a street name and a house name. Just as all houses in the same street share a street name, all computers on the same network segment share a network address. And just as a house number is unique to each house on a street, the host address is unique to each computer on a network segment. Routers use the network address to move network packets to the correct network segment, and the host address is then used to route packets to the correct host on that network segment. IP addresses differ from mailing addresses in one important aspect though. With a mailing address, you always know which part is the street name and which part is the house number. With IP addresses, it's not obvious which is the network address and which is the host address. The only thing we know is that the first part is used for the network address and the last part for the host address. But from looking at an IP address alone, we don't know where the network address ends and the host address begins. To provide support for very big networks as well as very small networks, we can change how many bits are used for each part of the address. For example, we could use only the first 8 bits for the network address. This would give us 256 possible networks. 256 is how many unique binary numbers you can create with 8 bits. Each of these would have 16, 777, 216 separate hosts. 16777 is how many unique binary numbers that you can create with the remaining 24 bits. On the other hand, by using the first 24 bits for the network address and the remaining 8 bits for the host address, you would end up with 16 777 216 networks, each of which can have 256 unique hosts. If you find all this stuff about how to figure out a network address confusing, that's understandable. It's confusing without our remaining piece of information, the indicator of where the network address ends and the host address begins. The piece of information is called the subnet mask, expressed in binary numbers. A subnet mask always has ones in the beginning and zeros in the end. When you line up a subnet mask with an IP address, the location of the ones shows you part of the IP address that specifies the network, and the location of the zeros shows you which part is the host address. For example, consider the IP address 192.168.1. 255.200 and a subnet mask of 255.255.255.0. When you convert these to binary, you end up with the following. So you can see here. So this is the binary equivalent for 192.168.1.20, and this is the binary equivalent for 255.255.255.0. To get the network address, you use part of the IP address that lines up with the ones in the subnet mask and replace the remainder with zeros. In our example, the network address is 110.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0.0. When you convert this back to decimal numbers, you end up with the network address of 192.168.1.0. The host portion of the IP address is the part that doesn't belong to the network address. In our example, this is 11001000 binary or 200 decimal. Private IP addresses. Some ranges of IP addresses are reserved and not assigned to any computers connected directly to the internet. These addresses are allocated for use only on private networks and between computers that aren't connected to the internet. These private IP address ranges are 10.0.0.0, 10.255.255.255, 172.16.0.0, 172.31.255.255, and 192.168.0.0, 192.168.255.255. Using addresses from these ranges for the computers within an organization's network means that you don't have to allocate any of the increasingly sparse regular addresses for all computers. You also increase security because a hacker can never send network packets directly from the internet to a computer that's inside a network that uses private addresses. A similar type of address is one that's assigned by automatic private IP addressing, AP. IPA is a feature of some operating systems, such as recent versions of Windows, which randomly assigns an IP address between 169.254.0.0 and 169.254.255.255 to a computer when this computer is not configured with an IP address and can't acquire a valid IP address from a dynamic host configuration protocol DHCP server on the network. Such IP addresses allow computers in a small network to communicate with each other even without any IP configuration. What about legitimate incoming network traffic? And what about people inside your network who want to establish a connection to a computer on the internet, such as a web server? You can allow for both of these scenarios by using a technique called network address translation, NAT. NAT keeps track of all the internet connections and changes the headers of IP packets to allow them to travel to and from a network that uses private IP addresses. The anatomy of an IP packet. All traffic that uses TCP/IP utilizes Internet protocol. As you saw when we examined the different protocol layers, the internet layer is responsible for addressing network packets and getting them to the correct destination. The protocol that is used for this is IP, just as every letter has an envelope with address information. Each IP packet has a header that contains information about the recipient and the sender. Unlike envelopes, though, IP packets don't need postage to be delivered, so you never have to worry about running out of stamps. Take a look at some of the information in an IP header. Source address. The source address is the IP address from which the packet originates. It's like the return address on an envelope sent by postmail. Generally, you can find out where the packet originated by looking at the source address. However, just as you can't absolutely trust the return address on an envelope that you receive in the mail, source addresses may not reveal the correct sender. When does an IP packet not contain the correct IP address? Here are the benign and the not so benign reasons. Network address translation, a technique that is used to send all traffic from an internal network to the internet by using a single public IP address. Many firewalls employ NAT to hide the actual IP addresses of internal computers. Although NAT may prevent you from tracing the origin of a packet to its original source, you can at least trace the packet back to a legitimate source. Spoofing, a technique that is used by the bad guys. Hackers may send IP packets with a forged IP address to hide their location. For example, if you were a hacker and intended to crash someone's computer, you wouldn't want your victim to trace the attack back to your computer's IP address. Destination address. A destination address is like the address on an envelope. Each router on the internet through which the packet passes looks at this address and dutifully delivers it to its final destination. Just as with the source address, NAT may translate the address on its way to the final recipient. However, you normally don't have to be concerned that a hacker may spoof the destination address. After all, the result would be that the packet doesn't arrive at its intended destination, which would be rather pointless. Transport layer protocol. An IP packet contains information about the transport layer protocol that the packet should be routed to after it arrives at its destination. This information is needed by the TCP/IP protocol stack, a fancy term for a part of the networking software on your computer that processes all TCP/IP requests to determine how the packet should be further processed. The most commonly used protocols in this category are TCP and UDP. ICMP, Internet Control Message Protocol. ICMP is an internet layer protocol that is used to confirm that two hosts can communicate with each other. Devices that use TCP/IP also use ICMP to inform other devices of potential problems. For example, the ICMP source quench message is the TCP/IP equivalent of telling another computer, I can't keep up with all the traffic you're sending me. So I'm going to leave it here today for this video. Thank you for listening and have a good evening.